Welcome to the lesson on the application of electrical laws. By the end of this lesson, you will be able to explain the underlying principle for an electrical circuit, which involves understanding the flow of electric current and the relationship between voltage, current, and resistance. You will also be able to identify the essential components necessary for a circuit to function properly, such as a power source, conductors, and a load. You will gain knowledge about the different types of loads in a circuit and how they affect the circuit's behavior. Finally, you will be able to illustrate a complete circuit, demonstrating your understanding of how the components work together to allow the flow of electricity and perform useful work. The application of Watt's law is instrumental in various aspects of electrical engineering. It enables engineers and technicians to calculate power usage in a circuit from known current and voltage, providing important insights into energy consumption. By ensuring that components operate within their power ratings, Watt's law helps prevent overheating and damage, thus contributing to the safety and reliability of electrical systems. It enables technicians to calculate the energy used in kilowatt hours, or kWh, by multiplying the power in kilowatts by the time in hours that the appliance or device is in use. This knowledge helps in assessing energy efficiency, estimating energy costs, and making informed decisions about energy management in various applications, including electric vehicles and sustainable technologies. Let us explore the topic of electrical circuits. An electrical circuit is a complete path that electrons travel from a power source through a load and back to the power source as illustrated in the image. Essential components necessary for a complete circuit include a power source, providing the electrical energy needed to drive the circuit. Protection mechanisms such as fuses or circuit breakers ensure the safety and integrity of the circuit by safeguarding against overloads or faults. The power path establishes the route through which electrical energy flows from the source to the load, where it performs useful work. The load represents the component or device within the circuit that consumes or utilizes electrical energy. Equally important is the return path, which completes the circuit by allowing electrons to flow back to the power source after passing through the load. Additionally, a grounding system provides a reference point for the circuit's voltage potential, enhancing safety and stability. Together, these components form a complete circuit, enabling the transmission of electrical energy for various applications. Exploring the components of an electrical circuit within the context of automobiles, we begin with the power source. In conventional vehicles, a 12-volt battery system serves as the primary power source, providing electrical energy to various components. Under optimal conditions, a fully charged battery is 12.6 volts, but can reach up to 15 volts based on battery type and charging system. However, it is essential to note that the electrical system requires a minimum of 12 volts to function efficiently. To maintain the battery's charge and ensure continuous power supply, a generator or alternator that is coupled to the engine is employed, which is responsible for charging and sustaining the battery's electrical potential. In automotive electrical systems, the power source plays an important role in powering up and maintaining the vehicle's vital functions, such as vehicle ignition, heating, ventilation and air conditioning, safety systems, etc. Another component of electrical circuit is the circuit protection. Circuit protection mechanisms are essential in preventing overheating of electrical wires, thereby minimizing the risk of electrical fires or damage to vehicle components. Common examples of circuit protection devices include fuses, circuit breakers, and capacitors. Together, these protective measures contribute to the safety and reliability of automotive electrical systems. Fuse boxes can vary in location in the vehicle. Always refer to the vehicle manufacturer guide for the correct location. In this image, the fuse box is located under the hood of the vehicle. Let us now discuss about the three types of circuit protection devices. Fuses play an important role in safeguarding automotive electrical systems from excessive current, protecting the circuit. Employing a metal wire or a strip that melts when exposed to elevated currents, fuses are designed to interrupt the flow of electricity and prevent damage to vehicle wiring and components. Once a fuse is activated due to overcurrent, it becomes a one-time use device and requires replacement to restore circuit functionality. The selection of fuses is a critical aspect of automotive electrical design, as they must be carefully chosen to match the specific current capacity and voltage requirements of the circuit they protect. Too low a rating may result in frequent and unnecessary fuse blowouts, while a rating too high may fail to adequately protect the circuit from overcurrent conditions. Circuit breakers represent another critical aspect of circuit protection within electrical systems, offering automatic intervention to safeguard against damage caused by excess current. These devices function as electrical switches, and they detect overloads or short circuits, promptly interrupting the flow of current to prevent further harm. Notably, one significant advantage of circuit breakers over fuses is their ability to be reset after tripping, offering convenience as compared to one-time use fuses. Circuit breakers are not commonly used in traditional automotive electrical systems. In most automotive applications, fuses are the primary form of circuit protection due to their simplicity, cost-effectiveness, and reliability. However, in certain specialized or high-performance vehicles, circuit breakers may be utilized in specific applications where higher current capacities or the ability to reset the protection device is desired. For example, circuit breakers may be employed in custom-built or modified vehicles with aftermarket electrical systems, or in recreational vehicles and trailers where higher electrical loads are common. Capacitors are another type of circuit protection device. These devices act as temporary electrical energy storage devices and release it as needed. By distributing charged particles across two conductive plates, as shown in the image here, capacitors create a potential difference that helps regulate voltage levels, smoothing out voltage ripples and ensuring stable electrical supply. Unlike batteries, capacitors charge up quickly and can discharge energy rapidly, making them ideal for applications requiring quick bursts of power. In cars, capacitors find widespread use in audio systems for filtering out noise and improving sound quality, as well as in ignition systems and engine control units to ensure smooth operation and efficient performance. Electrical loads serve as essential components within electrical systems, playing the role of consuming electrical current and converting it into various forms of energy such as light, heat, or mechanical motion. These loads are integral to the functionality of electrical circuits, as they enable the transformation of electrical energy into useful work. Without loads, the voltage supplied by the power source would have no purpose or application, as there would be no need for electrical energy to be utilized. Thus, loads are indispensable elements in electrical systems, serving to fulfill a wide range of functions across numerous applications, from powering household appliances to driving motors in industrial machinery. A few examples of electrical loads in automobiles are illustrated here. These include light bulbs, resistors, horn, entertainment radio, resistors, drive motor, cooling fan, etc. In an electrical circuit, a ground serves as a reference point or return path for electrical current. It typically refers to a conducting connection, such as a metal rod or a copper wire, that provides a low-resistance path to the earth or to a common reference point within the circuit. A ground is essential for purposes such as circuit safety and protection, and as a reference point for voltage measurements. A common ground in electrical circuits refers to a shared reference point for all ground connections within a circuit or system. Instead of having separate ground connections for each component or load, a common ground allows multiple ground connections to be connected to a single point. This simplifies the wiring layout and reduces the complexity of the circuit. In a common ground configuration, all ground connections ultimately lead back to the same point, typically the negative terminal of the power source or a designated grounding point on the circuit board or vehicle chassis. Common grounds are commonly used in various electrical systems, including automotive, industrial, and household circuits, to streamline wiring and ensure proper operation. The ground port in multimeters, often labeled COM for common ground, reflects the widespread use of this concept in electrical measurements and diagnostics. Let us now summarize what we have learned in this lesson. A complete electrical circuit requires 5 main components to function effectively. Circuit protection is critical to safeguard against excessive current and prevent damage to components. Loads, which comprises of various devices such as headlights, radios, and motors, serve as the recipients of electrical current within the circuit. A common ground is essential for vehicle wiring, with the chassis often serving as the conductor to achieve this connection. Overall, understanding and implementing these key components are fundamental for ensuring the safe and reliable operation of electrical circuits, particularly in automotive applications where efficiency and safety are prime concerns. Thank you.